Hello, everyone. Today I'm going to talk about kernel matrices in machine learning and some linear algebra problems. This is joint work with Josh Emmon, Tim Chu, and Aaron Shu. And this work was done well, like Josh and Aaron and Tim when we were visiting Berkeley last year. And I will start. So I'm going to talk about some kernel matrices and from several different perspectives. I will give you the motivation of why do we study this problem. For example, there are some physics problem people care about kernel matrix times a vector, and also in machine learning, especially in deep learning theory, there are some neural tangent kernel popular stuff going on now. And at the end, I'm going to tell our main results about kernel, linear algebra stuff. And for example, if I give you a matrix, kernel matrix and a vector, and how fast you can multiply these two. And also, if I give you a kernel matrix kind of linear system, how fast can you solve it. And also, if I give you a graph which is implicitly defined by a bunch of points in Euclidean space, and how fast can you sparse that graph. So I will start with the physics motivation, and the original plan of is we are trying to understand universe, and single we have a solar system, and this is a gravitational bound system, and there are a lot of stars in the system, the biggest one is the sun, also there are some small ones, they are orbits around the sun, and there's 8 big ones. And also there are some other stars, and they are orbits on the sun indirectly, like moons. So one task you are hoping is the following. And if I give you a bunch of stars in the universe, and you look for one star, and you want to compute the gravitational force of all the other stars induced on this star. Here is one well motivated physics question, and so the task, if you can actually define the task in the math way, and we are just give endpoints in d dimension, and in universe we put think d is 3 or 4 if you count time, and the goal here we just simply go I remove some gravitational constant, then you should think v is some fixed star, and you want to compute all the gravitation induced on this v from other stars. And then you basically look at these summation terms. And you actually want to compute, your goal is actually compute for all the u. And naively, if you have n points, and then if you just do naively, it will take n squared time. So more formally, you can define a problem following a symbol function fz, and which is 1 over z. And now you define an f graph. This f, you have a graph. And the graph is based on two things. One is a set of points. The other is based on a function. And now you can actually, you have a vertex set. For each Euclidean points, for each Euclidean point, you can actually single there the vertex in your graph. And now I'm going to define edge weight of this graph. And this graph will be very dense. So for every two pair of nodes, you can actually define their weights based on this function f of L2 norm squared, the distance between u and v. It's very different from a classical graph problem. In classical graph, we actually the graph can be very sparse, and sometimes people care about some running time, depending on m, vary the number of edges in the graph. But in here, the graph is very dense, it's always n squared. So you can write down the adjacent matrix, which is a very dense matrix, has n squared size, and every entry is non-zero. And my goal is the following. I want to compute ag times y for any arbitrary vector y. My claim is my goal is trying to do it in almost linear time, which means I'm not allowed to spend n squared time because this is very true. My hope is to getting n to the 1 plus more 1 time. This is this idea is original from physics people, and they call a fast multiple method, and it's proposed by Laplacian Greengard and Van Rocklin. It has been existing for a very long time, for almost 30 years, And at the beginning, like they also use this method to compute some like gravitation, like the force between the particles in the small world, because they have so many particles, and you are just unhappy with like paying n² time. So this method like become very popular, and someone write down a list of like top 10 algorithms in last century, and this algorithm is one of them, as you can see. And next from the talk, I'm going to like motivate why do we study the kernel from the machine learning perspective. So in machine learning, like we usually have some Gaussian kernel, and sometimes we want to do classification task instead of like working on linear like space.
Sorry, what does that do with multiple? What's the kernel?
Once you have a kernel function, and you can write down a kernel matrix. And
you can apply multiple to this kernel.
When you want to multiply a kernel matrix with a vector, you can apply fast multiply method.
Fast?
Yeah, you can apply the fast multiple method, but that only take like a near linear time, not n² time. Yeah, there could be some potential use in machine learning. So, yeah, there are some famous paper by like Berkeley group. They study some like spectral clustering that uses Gaussian kernels. And also like some like random Affiliation papers, they also use random kernels. And recently there are like some breakthrough like in deep learning theory. They use something like called like a neural tangent kernel. It defined in the following way: for any like input vector u and v, you should think of u and v are like input data points from like neural network training, and w is like your weight. You should think of your weight matrix in infinity base. And now take integration over like from like w from some distribution, and this sigma is some activation function, and sigma prime is just a derivative of the like activation function, and that's why we call like a neural tangent kernel.
So this is for one gate. Neural tangent kernel for 1 gate.
What do you mean 1 gate?
I mean, neural tangent kernel can be defined for any network. Right?
Oh yeah, I'm just talking like the wire. Yeah. Yeah, I'm just for the simple case, yeah. And this is originally defined by Jack and Gabriel 2 years before. And their long level work, they are trying to like analyze the convergence on deep neural network. Like if you assume data separable, and the neural network has a sufficient width, large width, and you run SGD or gradient descent, you can actually find a global minimum. So most of this works, they either like implicit uses kernel, or they actually implicit uses kernels. There are also recent work by Sanjeev and Du and Hu and Li and Zhao and Wang, and they prove actually infinite neural network is actually equivalent to like a kernel regression. Recently, I'm also working with other persons, Jason and Ruoqi and Mengdi and Zheng, and we actually show like even you add the regulation term, and they have like they also have some equivalence in some certain way. Yeah, this is just a motivation of this is like the kernels in machine learning right now. And here is like the formal definition I'm going to define for you. Like sigma denotes the activation function, and suppose this is just a loop. So sigma z is going to output the max between z and 0. For each point, every point, we define mapping, which is the integration. And if you give like me like n points, I can actually write down a kernel matrix for you. And in last year, there is a very important work by Du, Zhao, Paulson, and Singh. They actually show some like interesting thing for this kernel, like if you compare the continuous case and the discrete case. So here I'm going to define like two kernels, and in their paper they call like H infinity, but here I'm calling it like a discrete and continuous. So the kernel like H continuous is defined based on like you take the integration over like a W from like Gaussian distribution. And here I'm just replacing a sigma prime by the ReLU when you take the derivative. And from another perspective, you can also like when we train neural network, our width is actually not like infinity, and we can also write down like the finite sum of this thing, and then we can define like a discrete expression of kernel. So the interesting is if you use lambda to denote the sigma, the minimum eigenvalue of this continuous kernel, and then you can show like if m is sufficiently large, and the smallest eigenvalue between these two, the eigengap between these two, like a discrete version and continuous, that's almost the same. And this is like a very crucial in their like analysis in the proof. And here, like the intuition is like you look at this matrix and entries, and every entry is more like a summation of m terms, and then you can apply Kernel bound to bound each entry, and with high probability. And now you just apply union bound all the n squared points. You can actually then you can take a summation of all the n squared values. You can bound the entire like forbidden zone. That's roughly how the proof goes. And they not only need this, they also need to show something like if you look at kernel like definition, they also need like if a matrix W is not moving too much, then my kernel matrix and my kernel is also not changing too much. Because in the entire like all penetration theorem, and they assume like as long as they need to like they first choose random W, and over all the training steps they need to use the randomness of W. And if your W is moving too much, you just cannot use the randomness anymore. So here like R is like a radius and like between 0 and 1, and I'm defining kernel based roughly the same as before, which is a discrete version. And here the statement is if I'm choosing like a bunch of random W tilde, and then I can argue like for any like W within small radius of this W tilde, if they are close to W tilde, then like with high probability, like the forbidden zone between these two are very small. So the programmers work, they actually just focus on getting this result. They don't care about if the analysis is tight. They pay some n square, and also they pay like a 1 delta here, and their probability is not like very high. So in our paper, like we just slightly improve the like a bound a little bit to make it tighter. And these are the two like a main theorem like in the like crucial like a very crucial in the analysis of like when you like train a neural network and to show it works. So finally, like if you do like more other works like analyze the gradient flow and something else, you can actually show this theorem, which is saying like if m is sufficiently large, and then the gradient descent algorithm, it can find the global minimum for this neural network training, and from some random initialization with very high probability. The first this type of result is proved by Yuan Zhi and Yingyu, and at the beginning they only prove for like stochastic gradient descent, and they are like m is very huge, and then like Simon et al. They actually show you actually only need m roughly equal to n to the 6. And with slightly string zero analysis by showing like you only need to pay like n to the 4th. So it's unclear like what the right m here should be. Someone conjecture like it should be maybe just like near linear, and this is still like an open question. Like we don't know how to do it. So the hope is like in neural network training, like this kernel matrix play a crucial role, and it's possible like when you design some algorithm, like if you can speed up kernel vector multiplication, then you can also possible to speed up the neural network bank propagation step. So next, I'm going to like give you some start like the problem like from a numerical linear algebra perspective. And I will first tell you like roughly what's the result. Like if I give you points in like a d dimension, so there are n points, and I can define graph. And if I give you a function, and I'm using the function to denote the weight, like for any like two input of u and v, I'm going to define the weight of the edge. The weight between the edge u and v is going to be f of L2 norm square of u minus v. As you can see, this graph is going to be very dense, has n square edges.
Okay, question.
Yeah.
So now you're going to be doing these approximations, right?
Yeah.
U minus v square is 2, but u in a product with v is tiny. So which are you going to approximate? Right? I mean, whether you approximate multiplicatively u minus v or u times u.
Eventually, the error I'm going to get is additive error. But
It's additive.
Yeah, it's additive error. Yeah.
But yeah.
For some cases, for some like a special kernel, I can do exact. But for some kernels, if I get error, usually I get like additive error. But the error dependence is very nice. You only pay log of 1 over epsilon, where epsilon is your error. So
Okay, sure.
yeah, you are not getting polynomial dependence over the error. Yeah, that's a good question. Yeah. So now I'm going to let LG define the Laplacian matrix of this graph. I will give you example soon. And let the adjacency matrix, let AJ denote adjacency matrix. And notice that if you write down your Laplacian can be written down be the diagonal matrix minus adjacency matrix, where diagonal is the degree, each entry is the degree of this graph. So here I just give you a concrete example of how we define Laplacian and adjacency matrix. Suppose G, like if I give you a bunch of points, and they're going to give you suppose they're going to on direct graph, and this is very may not be dense, but here I just give you a practical example. Suppose we only have 5 nodes and 6 edges, and here example where AJ looks like this matrix, and AJ is going to be a symmetric matrix, and the diagonal entry is going to be 0, and any place like AIJ is equal to AJI, and the matrix D is going to be a degree matrix, and is going to be each entry on diagonal is going to be summation of the one row of the original matrix in AJ. Then the Laplacian matrix is just going to be defined to be the DJ minus the AG. Okay. So our result is following. We first focus on matrix vector multiplication task, and suppose I give you arbitrary vector, and the question how fast you can approximate LJ times y, or how fast you can approximate AJ times y. And my goal is I don't want to write down n square matrix. So in the paper we actually can show these two problems are actually equivalent. And we also want to do something called spectral graph specification. You give a dense graph, I'm going to output a very sparse graph for you, and they are very close in spectral sense. For example, if I give you a graph G, and the LG is Laplacian of matrix of G, and I'm going to output a graph H, and such that the Laplacian of matrix of H is going to be 1 plus minus epsilon close to the LG. And in the meanwhile, we hope the size of this, the number of edges in the H is going to be very small, n log n or epsilon square. So the point is the original graph could have n square edges, but now I'm slicing graph to roughly n log n edges. Yeah, here for spectral specification, we can do relative error. We are not going to give you additive error. And another question called Laplacian system solving, and the problem is roughly following. If I give you you should think you want to solve a linear system which is LG times y minus b, and then a trivial solution should be just y equal to LG pseudo inverse times b. But I don't want to write down LG and then take a pseudo inverse. I want to do something smart, and the whole of all of these problems, and we can actually figure out some property of this function f. So eventually we can say if function f has some nice property, for example multiple Lipschitz, I will define later. And so we can show if f has this property, then for most of these tasks you can actually spend only an almost linear time, n to the 1 plus 1 over 1 time to solve the problem. From another perspective, if your f doesn't have any some of this good property, and then if you assume a strong ETH, and you can show for most of these problems you have to take n squared time. Here is the rough result. I'm going to print the rest of the talk. So the main game of this problem is you want to improve the quadratic to linear. And here just a true example. I give you a bunch of dots. I draw a linear line here, and I also can draw a quadratic line. And so the question is where is this matrix vector multiplication in this figure? It takes either n squared time or it takes linear time. And like this, and also for specification, and also for Laplacian system solving, and we want to figure out where is the runtime in the picture. So we are going to study this problem from two perspectives. And so first I will give you some definition. Like alpha is some like maybe called stretch factor of the graph maybe. It's more like the maximal weight divided by the minimal weight. And the epsilon is accuracy parameters. And we actually need to like separate two cases. One is when d is small, is like below log n. The other like case is d is roughly log n. Because sometimes when d is smaller than log n, and you can actually do some brute force like pay 2 to the d time, and then this is just to be very small, not going to give you a square. But when d is roughly like theta of n, you cannot do this stupid trick like 2 to the d time. So the question we want to ask is there some like a runtime like based on poly d times log n with some accurate parameters, also times n to the 1 plus small 1 time. And similarly, like for d equal to like small log n, we are okay even with paying like exponential in d. Because in this case, like for example, in d log n, like this log n to a log n is still going to be much smaller than n to the small 1. Yeah.
D is?
So d is like a data dimension. Like
Oh, I see that.
Yeah.
But for kernels, that's D is low.
So like for neural network training, d is just the image size. Like how big is the image? It's also depends how to write a kernel, but naive thinking is.
I mean, the point is like sort of the kernel embedding of.
No, it's not. It's not an embedding. It's just the d here is just directly be the like input data points in the neural network training. I think it's just the image length. You can do it naively. It's also working.
So wait, so what's the matrix you're multiplying? So can you map the Laplacian thing to the matrix? So like maybe you can use a board. So if you're trying to do like kernel regression, is that right?
Yeah.
How would that map to your framework?
So the point is the kernel regression has like closed form directly. And I'm afraid that you can there are some ongoing with Jason and some other students, and we are trying to like extend the kernel, like your paper, like a kernel regression with like the equivalence like from kernel regression to infinite neural network training to a regulation term. And for some reason, like a kernel regression, you have a closed form, and doing this thing is not like it's unclear. Is like the necessary way to do it? It's unclear if it's efficient or not.
No, I'm not even sure what the mapping is.
So
what's the matrix?
so
you have a kernel. Let's say RBF kernel. Doesn't matter. Simple kernel, not anything.
yeah. You need to map. Okay, this is like points, and you can write down a kernel like which is like let's call it like a H. Like Hij is going to be the k of xi. In our case, we just write this way. So if you assume like all the data points they are in like units for, and this any of this kernel for neural tangent kernel, you can actually write this way. Okay, and okay, now you have this matrix H, and you are going to write down as like a matrix from like phi times maybe phi transpose times phi. Okay, or maybe write it the other way, and the phi matrix is going to be like n dimension times infinity. And like when you do like kernel prediction, you're more like thinking you are doing like an inner product with like this phi with another like you should also think of like this phi as a function. Like there are some like a test vector, and also like there are some like there are training data. You're more like look at inner product of these two and doing a prediction.
Yes.
That's how you do it.
So you're applying it at test time, meaning at inference time.
Yeah, yeah.
I see. So then the points have been embedded already, and the inner product is already there.
Okay, so the interesting of this regime is you can actually the point is you can actually they actually support some online like all like thing, and you can actually pre-process the data and compute this one, and for anyone on the flight you see that you can actually spend like a very short time, like polylogarithm time even.
I see. And the matrix you are working with is that H matrix?
Yeah.
That's that matrix.
Yeah.
But
Yeah, the matrix in the talk is this H matrix.
and it boils down to matrix vector multiplication.
Yeah. It's not exactly, more or less you are multiply like this phi is not like exactly this H, but it's some there are something like a non-trivial going on, like I can even after talk maybe. Yeah, it's kind of complicated. Yeah, the connection is very complicated. Yeah, yeah. I just trying to work on this thing like from a few months back. Yeah. Okay. And first, I will print the result about like a matrix multiplication, and the task is you give a matrix, and a vector, arbitrary vector, and go to compute this A times Y, either exactly or approximately. So usually we know like if A and Y are dense, and if you want like exact solution, you have to pay like a naive time, like n squared time. And however, like if A has some structure, you can hope to do better, which is sublinear in square. Like for example, if A is a Fourier matrix, you can just do Fourier transform and take n log n time. If A is a Hardness matrix, you can also do the same thing, pay like n log n time. And if A is like some circular matrix, this is corresponding to some convolution like operation, you can also hope to do like n log n time. And the question we are going to answer, we are trying to answer here is like what if Aij is some like a function of like L2 square of xi minus xj, and then what's the runtime you need to pay? So here I just give you like a rough like interpretation of the theorem look like. What theorem look like? You should think of like f is some function which is like think of this is like analytic is something called like Taylor expansion ball somehow. Like we just need it locally Taylor expansion ball. And then I give you a bunch of points, and we just think about like worry about like a high dimension for now, and when d is like log n. And then we can define a kernel and mapping, and for any input, for every two input, we can output a value. And then like the task is for any given vector, and the goal is we want to multiply give a epsilon approximation of Lj times y. So if f can be like so if f has some like certain like nice property, for example, f is very close to some polynomial, and then the problem can be solved actually in n to the 1 plus small 1 time. And otherwise, like if you assume ETH, and the problem like is going to require like n squared time. For more like for low dimension and for other tasks, we also like characterize some like a general property called like multiplicative Lipschitz. And we are going to say like for some function, if you have this property, you can do it in like a near linear time. If you don't have this property, you need to pay like n squared time. So the property is defined in the following way: I give you a function f. F is the mapping from real to real, and we call it CL like multiple Lipschitz. if for all the x and for all the row in this one over c and c, and the f row of x is most c times l, c to the l times fx, and also at least c to the negative l times fx. You should think like this function is not going to be jumping too much. Like here are some examples. For example, polynomial satisfy this property, and one were polynomials, and this one also. And but like e to the negative x and e to the negative x squared, they are not going to satisfy the property. So note that like if you look at a Gaussian kernel, they are not going to satisfy this property. But actually we have some other way to do it. Yeah, this is something we defined, but it's actually, if you look at some other papers before, for some other problem like nearest neighbor search, or like linear regression or rank approximation or k-means, they actually define some similar thing, but they don't call it the same name, but they have some similar like. So it allows you to bound changes in. It's more like more like you bound to like when you bound the, you don't want to the function growing like very quickly. I think in Lipschitz you are even more like a. Don't worry about it. It's not essential. No. It's okay. So I think in Lipschitz they are more robust. Like your function mapping could be mapping from like a vector to a vector, and then you bound out and like a. But in here, like we are very restricted. We have to be a function mapping from a scalar to a scalar.
Lipschitz of the log would be f to the power. And this is not a
Yeah, I think so.
Yeah, I guess I'm just thinking of f of x.
This should be additive. This should be additive.
For low dimension, we can use some like some method called like a fast mod method. So for this, like there's a few like there are a lot of papers working on this kind of problems, and but if you look at this field, like one issue is like every paper they are only focused on very specific kernel, because they only target on very specific kernel like a matrix, and for some specific applications, and there is no unified paper to actually unify, like there are paper to say like for what kind of class you can do it, for what class you cannot do it. So our paper is the first paper like we are trying to unify all the papers like in this field somehow. So suppose like fx is equal to x to net x, and then you consider a problem like you're given like x1 to xn as some input, and they're going to define a kernel matrix as a graph, and for any vector y, we can compute epsilon approximation. Epsilon means like you pay additive error on every coordinate, and you just want to approximate ag times y, and this takes only like n times the log to the O of d time. So basically, like when d is very small, like log n, just take it roughly like n to the 1 plus more 1 time, which can be much faster than n squared time. So the general idea behind this algorithm is they need a function to be like a tightly expansionable, and they also need some like geometry idea like they can actually group their idea more like they are like cutting the infinite space into like a log of 1 epsilon to the d blocks, and then look at all the points in each block and trying to compute the influence between the block by blocks. Now trying to compute the influence between points and points, and that's why they can reduce the n squared to this n times log to the d. More interesting, we can show some hardness result. This is also not known before. And we can show like if your function is not this kind of Lipschitz, and then actually if you assume a strong ETH, and also your dimension need to be like c to the log star n, and then there are no like subquadratic time to solve this problem. So next I'm going to go to the graph simplification. So if you give a graph and a Laplacian matrix, and the goal is to output the graph H is such that you want LH is spectral close to the LG. And you also hope like the goal of this task is you want to spot that graph where make sure the L0 norm is small. And there are some deterministic algorithm, and you can do some famous BSS sample. You can get down to n over epsilon square edges, and this is also tight because they are lower bound. And there are also some randomized algorithm, and you can like sample each edge independently, and according to some potential function, you can eventually get a spatification. Also, you can actually sample a bunch of random spanning trees and add them together. You can also get it. So in here, our task is we don't want to write on a graph. We don't want to write on a matrix. We want to get like sublinear in subquadratic time. So we need to use the same Lipschitz definition as before. And we also need like the weight ratio. Like this is just this is necessary in some sense because you have to do the binary search between the largest bit and smallest bit. Eventually, we will just pay a log of this alpha. So from algorithm perspective, we can show like for any 2L Lipschitz, you can actually pay some running time like 2 to the root L times the small factors, and you can actually get down to like n log n edges. And from a hardness perspective, we can show actually this like L is necessarily independent, and by assuming like a strong exponential time hypothesis. And similarly for low dimension, we can get an algorithm where you take like L to the D, and from the hardness perspective, we can show like if your dimension is like a C to the log star n, and you have to pay like L to the C prime time. Yeah, at the end, I will give you some quick like a view of this solving Laplacian system. And it's known like for like just to solve a linear system. You don't have any structure or matrix, you have to pay n to the omega time. But if you have some structure, like a graph structure behind this matrix, you can actually only take like m, like a near linear time in m, where m is the number of edges in the graph. So they are long line work. They are trying to improve the running time, the solver of the Laplacian system. And the question here we are trying to ask is whether we need like for what kind of function we need like the subquadratic time for what kind of function. We have to pay like n squared time. So here is just the history of the Laplacian system solving. And that m denotes the number of edges in the graph, n the number of nodes, and the epsilon is precision. And then like at the beginning, they take like m times the log epsilon times the log of log 70 n, and then people can actually remove this lot. Currently, we only pick a root log n factor. We can really solve this. We can really solve this problem in near linear time by only pay an extra root log n. And in our case, like in our like a geometry graph case, where we have a kernel matrix and have a bunch of points from like a d dimension, and we can say like if f has some net property like this Lipschitz property, and you can do like a almost linear time. And if f is essentially bad, you have to pay. You cannot do this time. So here is like a concrete example, like for what kind of function we can do what kind of jobs. And for example, like the first function is fz is equal to z to the k, and also like e to the c, where c is a constant, and also e to the z, negative z, and also this is actually a neural tangent kernel in some sense. This is a threshold function, threshold kernel. And what we can show is like if the first column is the dimension, is from smaller to bigger, and the last 3 columns they are represent different tasks. If the function is in the table, it means we can give algorithm. If the function is not in the table, it means we cannot give algorithm. The blue one means we actually don't know right now. As you can see, like our algorithm can actually generalize can be used to do like for the Gaussian kernel, which is very, very useful in practice. And also can be extended to a threshold kernel, which is like for neural tangent kernel we can also apply. So here just a simplified version like how the theorem and I just give you like a very intuition like how the proof works. So let fx equal to 1 over x. and you have a bundle of points in D dimension, and this is your matrix A, and algorithm is saying we can actually only pay like n times the log to the D time, and give an epsilon approximation where you only pay actually in epsilon actually in log. And if you assume ETH, strong ETH, you can actually do it in, you cannot do it in subquadratic time. So in the rest of the talk, I will give some intuition of fast map method. So the linear like a function f has some like Taylor expansion type of thing. Like also you also need like when x is large and fx is actually small. This is same. This is true for Gaussian kernel. Another idea is they actually split the continuous domain into like a bunch of discrete points, like roughly 2 to the deep boxes. And for each core point, instead of computing the influence from this point to all the other points, I'm just computing the influence from this point to all the box, and which could be small. And here I'm just giving like an intuition of how do we prove hardness, and we reduce from like a bichromatic Hamming nearest neighbor search problem. And the problem you give like 2 sets, and they are like belong to 0, 1 to D. And the goal is to return you want to pick one point from A and one point from B to make sure their distance is small, the smallest one. And it's known that if you use localized hashing, and you can only like pay like n to the 1 plus O of 1 over C time from Indic and Montaro paper. And also recently like Avia Rubinstein and Ligia Chenich proved actually there are no subquadratic time if you assume for any constant epsilon, if you assume like a strong ETH. So our reduction is following. You think of like a g function, gx is equal to like x to the net take omega log n. And we are going to reduce from the approximate bichromatic near search problems. And here like the algorithm just more like a reduction of the algorithm. We want to compute, suppose we want to compute the cast size between A and B in the G graph. And the idea is if the mean distance is at most a k, then the cast size is going to be at least a k to the negative omega log n. And if the mean distance is at least 1 plus epsilon k, and then cast size is going to be at most like n squared times 1 plus epsilon k to the negative omega log n, because you can only have like n squared pairs. And eventually you can show like there are the 2 numbers that gap, then your reduction is going to work. So the key idea is like instead of like go from like a function g to function f, we assume like we can assess like a f k matrix like using like k plus 1 cost to compute like f matrix. So f to the k is like a derivative, the case derivative of this function. So then like we take the expansion of like 1 over x, and there is a linear combination of it by evaluating log n points, and basically just take log n terms, and then we can show you can from the product side f to the omega log n is equal to g, and then like because g is hard, then like f must be hard, therefore we prove the hardness. So here I just give you a summary of the talk. The fast method is a very fundamental algorithm. We gave the very first hardness. We also unified all the results, most of the results in the literature. And for a dense matrix that constructs from like n points in D dimension, and for certain tasks, it can be done actually in almost linear time. Like you don't need to pay like n squared time when the kernel function has some special property. And on the other hand, like also linear time algorithm only applies for certain class of commonly considered function. For some other functions, for some bad functions, actually you need like n squared time. Yeah, thanks. Any questions?